In computational dynamics, researchers hand their matrices over to Arnoldi iterative solvers, expecting them to faithfully extract the true decay rates of the system. Our previous scans of twisted Ulam matrices identified highly oscillatory wave packets buried deep within the spectrum. We tracked these structures, tracing their behavior across multiple parameter windows. Down in these deep tiers, the wave packets resolve into intensely localized, dense geometric shapes. They look exactly like stable spatial modes. But we have to test whether these deep spectrum structures are true physical geometry or if they are a mathematical mirage born from a computational trap. Certifying a numerical output based entirely on its spatial shape creates a severe blind spot in computational mathematics. To find out if these states are real, we have to look at both halves of the eigenpair. Non-normal matrices produce a right eigenvector, which maps the spatial density, and a left eigenvector, which defines the observable state. In a perfectly stable system, these two vectors align mathematically. They corroborate each other. This diagram shows the spectral condition number, kappa J. It measures a state's extreme sensitivity to numerical perturbation by taking the inverse of the dot product between the left and right eigenvectors. If the left and right vectors begin to rotate away from each other toward orthogonality, their dot product shrinks toward zero. When that denominator drops, the condition number grows exponentially. We applied this exact diagnostic to the executed Ulam matrices at the B2 spray point, specifically setting epsilon to 0.70. Without mapping this pseudospectral condition number, a researcher running an Arnoldi iteration is completely blind to underlying floating point collapse. We start by interrogating the dominant state of the system, tier 1. For this leading tier, the left and right eigenvectors maintain a tight structural alignment. The condition number for tier 1 rests at approximately 10 to the second power for both the WBA and Lorentzian kernels. In pseudospectral terms, this is moderate non-normality. The leading state remains computationally sane. Because this bounded condition number confirms that the algorithm is tracking a real mathematical property, the solver passes the surface-level test. This stability at tier 1 validates the methodology in the researcher's mind. It creates a false sense of security before they dig into the deep spectrum. Moving past the dominant mode, we descend into tiers 2 through 10. Down here, the right eigenvectors remain intensely localized, forming single-cell or two-cell spikes. This table logs the cumulative mass width, the K90 diagnostic, at a grid resolution of 16,384. The entire physical slit print of these wave packets collapses to a width of just 2 or 3 cells for both kernels. A spatial footprint this tight usually implies a strong, coherent physical resonance. A visual inspection of this tight spatial clustering would satisfy standard numerical expectations. A researcher would see these spikes and certify them as robust, discrete modes. But intense physical density does not equal numerical stability. The geometry is holding together, but the mathematics are failing. The terminal failure reveals itself the moment we calculate the condition numbers for these compressed spatial spikes. Non-normal discrete operators are subject to a mechanism called pseudospectral tearing. The right eigenvector, the physical footprint, stays completely localized, but the left eigenvector physically folds away from it. As they twist toward a 90-degree angle, their inner product shrinks to 0. The resulting condition numbers leave the realm of computational sanity. For the Lorentzian kernel, the condition numbers hit 7.1 times 10 to the 16th power by tier 3. The WBA kernel fails even harder. Its tier 3 condition number hits 2.7 times 10 to the 18th power. The vectors have fallen into an exceptional point trap, making the eigenvalues infinitely sensitive to even infinitesimal perturbations. The dense physical clusters we see on the grid are an algorithmic illusion. At these tiers, the Arnoldi solver is no longer calculating dynamic decay rates. It is tracing floating point noise. We applied a secondary independent diagnostic to corroborate this failure, running theta 3 and theta 4 partition probes on the highest risk tiers. This interface shows the output of those partition probes. The bins successfully record mass above the baseline threshold, but they completely fail the required Cliff parameter pass criteria. Failing the Cliff parameter confirms that these packets have no coherent multi-packet phase alignment. The internal structure is random. These probes strip away the last possible defense. These wave packets cannot be classified as structured discrete modes. The geometry and the partition data point to a singular conclusion. Without valid pseudospectral structure, these deep Ulam eigenvalues are functionally meaningless. These failures are strictly limited to the executed grids tested in the paper, specifically matrix sizes of 8,192 and 16,384. The scope of this breakdown is isolated to the B2 spray point at epsilon 0.70 for the WBA and Lorentzian kernels. These specific local failures cannot be extrapolated into continuum claims or asymptotic limits. Furthermore, the previously certified BV gap of 0.6509 remains completely untouched by the instability of these deep-tier modes. The takeaway is exact. In non-normal operators, a clean spatial spike in an eigenvector is insufficient evidence to trust the output of an Arnoldi solver. To safely extract data from these systems, researchers must map the pseudospectral condition numbers. Leaving the deep spectrum unexamined guarantees you will eventually mistake algorithmic noise for physical truth.